So here let's go through the stations in electricity and magnetism activity to see what you were kind of supposed to observe and how we explain that. So here's the jumping wire one, and of course the key here is in the title, that the wire jumps. Now, if I were doing this demonstration in class, I'd be able to talk more about it, but I mean, the idea here is that the yellow piece here is a wire, just bent into this shape. You can see the charges flow in one end, out the other end, and we know it's a wire with that eventually have current because when you close the switch, there's a current, shown here by the ammeter, so we know it's a conductor, okay? But what's interesting, and something I'd point out when we did this actual experiment in class, is that it is a wire made out of metal, and it's between the poles of what actually is a very strong magnet. The one we have in class is incredibly strong, and right now nothing's happening. That should be rather interesting and rather surprising, that it's a piece of metal and it's not attracted to or repelled by the magnet. Only when we close the switch does something interesting happen. So here's the observation, that when we close the switch, the wire jumps. And then when you switch the direction of the current one way or the other, then the wire jumps the other way, as shown by the positive current or the negative current, however you want to think of it, one way or the other, shown here by the ammeter. The point being, the observation is the wire jumps. Okay, so what's the explanation? Well, the wire only jumps, the wire only feels a force when the charges move. Even though it's a piece of metal, it's not attracted to the magnet in any way or repelled by the magnet until it has a current. And so really the takeaway here is that only moving charges experience magnetic forces. That's kind of what I was hoping for you to get out of this. It's interesting, and of course in class you would see it actually happen. It's very striking when you see the wire jump one way or the other. Alright, here's station 2. Really, all I was looking for you to see here is that this is sort of confirmation of the right-hand rule. Some students got a little bit confused, and I was maybe hoping you would get a little confused by seeing these black dots, and the black dots seem to be going the opposite way of the arrow. A good number of you figured out that the arrow shows conventional current. The black dots then, well, not too many students got that, but the black dots, what are those? They must be electrons. So this is showing the difference between conventional current and the actual flow of electrons. Remember, we only do conventional current, but still this is just showing that the electrons are flowing the other way. We know it's conventional current when we do our right-hand rule, and you grab it so your thumb is pointing the way the current is pointing, then we have confirmation that the field line surrounding this wire with current points the way that your fingers wrap around. So that's really all I was hoping for you to see here. Of course, also by moving the compass around, you saw that it sort of follows the field lines. That's really also what I was looking for. Also, really cool little detail here. Did you notice that in the person's hand with the nail polish in, that the red nail polish is the thumb, and that's the direction of the current, and the blue nail polish is the fingers wrapped around, and that's the direction of the field? They spared no expense in this particular simulation. Fantastic. On to station 3. Okay, so there's a lot of confusion with this, and again, this is the sort of thing that is much better seen live and in person, but here's the idea. They first put the compass here, and they showed that there was a magnetic field, and that's where some students got confused. There's a pole here and a pole here, which you can't see very, very well in this image, and even in the video it might be tough to see, but that's what the compass was meant to show. The meter over here is nothing to do with it. The meter is just there to connect to the wire and see whether there's current. But the compass that was put over here is to show that there is a north pole of a magnet here and a south pole magnet here. In fact, this is a horseshoe magnet underneath here, showing that when the person moves the wire, they're moving the wire through a magnetic field, which is shown by, oh, you know, the title and also the title of the video. You really should be looking at the titles of these. They really give you a lot of clues. Okay, and so the observation is when the wire moves, there is a current. This is an ammeter, which you know because it says microamps there. There's no confusion about that. Shouldn't be any. But what's so important, the other observation, is that there's no battery. So how are we getting current when there's no source of voltage? And that's what's interesting here. Okay, so we know that all magnetic fields come from moving charges. The universe seems to crave symmetry. So a lot of scientists thought, well, if current or electricity can create magnetism, maybe it can go the other way. And that's what we're seeing here. We're doing something with a magnet, and we're getting a current without a source of voltage, without a battery. But it only happens when the wire moves. So that's what's so important here, that if you watch the video again, feel free to go back and watch it again. When the wire doesn't move, this registers 0. It's only when the wire is moved up or down through the magnetic field that there is a current in the wire. So something interesting is happening here. We're sort of inducing, we're generating, we're creating a voltage, driving current through this wire, but only when the wire moves through the magnetic field. There's got to be some sort of change that's happening here. Okay, that's the important takeaway. That when we change something about the magnetic field, or we move the wire through this magnetic field, we induce a voltage, we create a current even with no battery. On to station 4. Oh, a generator. Again, we are creating voltage, and the takeaway here is that there's no battery. We're again getting voltage without a battery, but we're doing it by cranking this loop of wire. We're turning this loop of wire, and when we turn the loop of wire inside this external magnetic field, the voltmeter here is showing a voltage. And yes, some students indicate that the voltage is changing direction. That's, I guess, changing positive or negative, and that's good. You notice that the current was changing direction. But again, the really important part here to notice is that we are creating a voltage without an apparent source of voltage, without a battery. This is very, very interesting, that we're getting electricity from magnetism, which is great. And here we're just going to pause going through our stations to talk a little bit more about this, because really this is how all of our ways of creating electricity are done in our modern day. Let's just think about the ways we create electricity, like a power plant. Think about maybe like a coal-burning power plant, burning fossil fuels. And when they burn the fossil fuels, they create a lot of heat. So you know what the heat does? All it does is it boils water. That's what it does. It actually boils water, and then the water turns into steam, and the steam is channeled through pipes to then turn a turbine. And the turbine does this. It actually just turns a loop of wire inside the magnetic field, generating electricity. What about a nuclear power plant? A nuclear power plant uses a nuclear reaction. The nuclear reaction produces tremendous amounts of energy, tremendous amounts of heat. You know what the heat does? It boils water. That's what it does. It's the same idea. It boils water, creates steam. The steam is channeled to a turbine. It turns the turbine, which turns a loop of wire inside a magnetic field. And so those power plants are doing just this, turning a loop of wire inside a magnetic field. It's amazing. It's crazy. And that's how we create electricity. What are some other ways we have of creating electricity? Think about other methods, like a wind power, or a windmill, right? Windmill, you can literally see the wind pushing on the blades of the windmill, which is connected through a series of gears to a loop of wire sitting inside the magnetic field. So it's really just the same principle. What about hydroelectric power, like a dam? A dam, like a reservoir, holds back a lot of water, and then it allows the water to trickle. I don't know if you knew that, but actually that's what it allows it to do. It allows the water to fall, turning gravitational potential energy into kinetic energy, and the falling water hits a turbine, which turns a loop of wire inside the magnetic field. And so you can see that all of our modern conveniences, all of our modern ways of producing electricity are actually based on this connection between electricity and magnetism, which is really just turning a loop of wire inside the magnetic field. The only way of producing electricity I can't link to this is solar power, but we're going to get to that in a future class. Let's go on to station 5. So here we have these two rings, and you move the magnets back and forth, and a lot of you realize, of course, that when you do that, this ring moves and this ring does not. That's the observation. The other observation, of course, is that there's a crack in the ring. Now, I had this exact demonstration in class, and some students thought that maybe one ring is an insulator, there's a conductor. I will tell you that they're both conductors. They're made of the exact same materials. It's all about this crack here, that something happens, that when you move the magnet into or out of the loop, you're again changing the magnetic field through the loop, and what that does is that induces a current. When it induces a current inside this metal ring, that's moving charges. Moving charges create a magnetic field. It actually produces a magnetic field from the ring, which opposes the magnetic field of the magnet, and that's why it moves. They're actually acting on each other only because the changing magnetic field of the magnet creates a current in the ring, which creates its own magnetic field, which then acts on the magnetic field of the magnet. Why doesn't it work here? Well, because there's a crack in the ring. As this magnet is moved in or out, it's trying to move charges around, but with the crack there, it can't happen. We have a break in the circuit, so it can't create a current, which can't create a magnetic field, and so nothing happens. And then we get to station 6, the dropping magnets. Whew, you can watch this all day, right? And I actually do this one in class. It's amazing to watch. It blows your mind. And so what happens here is you drop the magnet in and it sort of floats on down, not picking up speed, not slowing down or speeding up. Why does this happen? So, all right, let's go through, and here I want you to maybe open up your notes and draw some pictures of this. So let's say here's the tube, whether it's a copper tube as shown in the video or an aluminum tube is the one I have in class. And here's the magnet, and you're going to drop it in. Let's say you just drop it with no speed, and so you might say before you drop it in, it has gravitational potential energy, obviously because you raise it up some distance, and it has no kinetic energy because you're dropping it from rest. In a normal situation, you would drop this, and of course by conservation of energy, it would fall and fall and fall, would lose gravitational potential energy, and pick up kinetic energy. That's the normal situation. Of course, that's not what happened in this mind-blowing demonstration. It floats down at a constant speed. So let's imagine there's some point P, and the magnet is falling past this point P sometime later, and it is losing gravitational potential energy, but it's not speeding up. That's the crazy thing. right? It's not slowing down either. It's just sort of flowing at a constant speed. So it's losing potential energy, but not gaining kinetic energy. This seems to violate the law of conservation of energy. But of course, that's a law. It can't ever be violated. So the question is, what's happening? How do we explain this? Maybe pause the video and give it a think through. Well, the energy's got to go somewhere. So let's see if we can connect this. In the previous station, you moved a magnet through a thin ring of metal, and what happened? Well, can you imagine that this tube, whether it's a copper tube or the aluminum tube I have in class, is really just a ring and a ring. It's like a stack of rings, just like in the previous station in the activity. What happened there? We created a current. So that's what's happening. This is the exact same thing as station 5. It's just a little more dramatic because you see the magnet just seems to be floating down at a constant speed. I don't know why it's happening, but it's about energy, right? So the lost gravitational potential energy by this magnet losing height transforms into kinetic energy of moving charges. If you were to connect an ammeter to this tube, you would actually register a current. Charges are moving around in there. And that's where the energy goes. So here we have conservation of energy. It's just weird that the magnet doesn't own its own energy anymore. It actually gives its energy up to the moving charges inside the tube, to the kinetic energy of those moving charges. Now you can also take this from a forces perspective, which a number of students did try to do in their explanation. Because you say, well, it's falling, so of course there's a gravitational force. Of course there is the force of gravity, but it's falling at a constant speed, which means the net force must be 0. So there's got to be another force pointing up. So the question is, what is this other force pointing up? Well, if you're thinking about all the things we've been doing here, it must be a magnetic force. So where's this magnetic force coming from? Well, put it all together, it's coming from the moving charges. Just like in the rings demonstration, or the rings simulation, once the charges are moving, that's a current. Currents create magnetic fields. So the moving charges create a magnetic field, which then applies the magnetic force to this magnet, which opposes the gravitational force, causing the net force to be 0, the acceleration to be 0, and it just falls at a constant speed, which is crazy and amazing. So continuing in our notes, let's just summarize these big connections between electricity and magnetism. We started off this whole topic by saying electricity is over here, magnetism is over there, and certainly they're not the same thing, even though there are a lot of similarities, and they really aren't. They really aren't. Magnets are not electrically charged objects. Magnets do not create current. Magnets do not have current. It's not about charge. There's something completely different. And yet there are these very deep connections between them, connections that we use to power all the things, or all of our modern conveniences that we have today. And one of them, of course, is that only moving charges experience magnetic forces. This was shown by station 1, that only when there was a current in that wire did it jump one way or the other, experiencing magnetic force. 2, this huge connection that moving charges create magnetic fields. In fact, this is where all magnetic fields come from moving charges. And 3, this symmetrical nature to this that goes the other way, that if you change something about the magnetic field, you create voltage, which again cause a current. So in statement 2 here, electricity creates magnetism. In statement 3, when you change the magnetism, you get electricity. And we're going to box all 3 of these in as big ideas connecting electricity and magnetism.